Now the last thing that we want to show you here in 7.8 is a particular comparison test for improper integrals. And the idea of this comparison test is that it gives us a way of determining whether a certain improper integral is convergent or divergent by comparing it with something that we already know. In other words, if we already know some other improper integral is convergent or divergent, then maybe we can draw a comparison with that known integral to say something about the integral that we're thinking about. And the theorem works like this. So if I've got two functions, f and g, where the f of x function is always greater than or equal to the g of x function, then if the integral from a to infinity of the f of x function is convergent, then the one that's smaller, the g of x function, must also be convergent. So the way you can think of this is that the area under the graph of f of x is finite, and therefore since the g of x one has a smaller area, it must also be finite. On the other hand, if we're doing it the other way, suppose I know that the g of x function, when I integrate from a to infinity, is divergent, then we know that the bigger function, the f of x function, when I integrate from a to infinity, will also be divergent. So again, here you can think of this as saying that the area under the g of x graph is an infinite area, and since the area under the f of x graph is bigger than the g of x graph, then its area must be bigger than the other graph, so it's also infinity. So it's important to think about whether we're trying to show convergence or divergence when we're doing this comparison. But let's just demonstrate with some examples. So in this example, we want to show that the integral from 0 to infinity of e to the negative x squared is convergent. And the reason why we might want to just compare this with something else is that the actual, we've shown previously that the actual antiderivative of e to the negative x squared is not something that we can express in terms of elementary functions. So this one is actually harder to evaluate directly. So instead, what we'll do is we'll try and compare it with something that we can easily evaluate and try and show that it's convergent, even though that won't really tell us what it converges to. It'll just show us that it is convergent. So anyway, what would be something that we can easily compare this with? And the idea is we want to compare it with something that we can easily evaluate. And, well, what would be easier to evaluate is to consider the integral from 0 to infinity of e to the negative x. This will be a much easier integral to evaluate than e to the negative x squared. This one actually is a very simple antiderivative. So how do these two functions compare now? Let's try and make an argument there. So we know that at least on the interval from 1 to infinity, so for x, let's say for x greater than or equal to 1, we know that x squared will be greater than or equal to x, and therefore negative x squared will be less than or equal to negative x, and therefore e to the negative x squared will be less than or equal to e to the negative x. So we see that if I can show that the integral from 0 to infinity of e to the negative x is convergent, then the integral from 0 to infinity of e to the negative x squared is also convergent, because it's smaller, has a smaller area than e to the negative x. Okay, now since here we were only considering x greater than or equal to 1, that will be sufficient here, because we know that from 0 to 1, this is definitely a finite value, because it's over a finite interval of negative x squared. So we can ignore the part between 0 and 1 and just focus on the integral from 1 to infinity. So in this case, the integral from 1 to infinity of e to the negative x, we can evaluate. So the limit as t approaches infinity of the integral from 1 to t of e to the negative x, which will be negative e to the negative x evaluated from 1 to t. And that will be negative e to the negative t minus 1. Or, sorry, e to the negative 1. So minus negative e to the negative 1. So actually plus e to the negative 1. Okay, now as t goes to infinity, notice that e to the negative t will go to 0. So what we've shown here is that this limit is equal to e to the negative 1. It's a finite value. So this shows that the integral from 1 to infinity of e to the x, e to the negative x is convergent. Okay, so since the integral from 1 to infinity of e to the negative x is convergent, and we know that what we showed up here is that e to the negative x squared is less than or equal to e to the negative x, then that comparison theorem shows us that the integral from 1 to infinity of e to the negative x squared is also convergent. Okay, now we've just shown it's convergent, but what does this integral actually converge to? That would be another question. Perhaps we would have to consider something a little bit trickier there in order to actually get the value of that integral. But here we know at least that that value exists. Let's try another example. Here we want to compare the function 1 plus e to the negative x over x with the function 1 over x to show that the integral from 1 to infinity of 1 plus e to the negative x over x is divergent. So now we're trying to show divergence. So we want to show that this integral here is actually bigger than something that is infinite. That will show that it's divergent. And we can easily see that here 1 plus e to the negative x over x has to be greater than 1 plus 0 over e to the x, or 1 plus 0 over x. Essentially here, adding e to the negative x to something in the numerator makes it bigger. So just getting rid of that term here, we get something smaller. And we know that the integral from 1 to infinity of 1 over x, we've shown this one already, is infinity, so it's divergent. Okay. So since 1 plus e to the negative x over x is bigger than 1 over x, and the integral from 1 to infinity of 1 over x is divergent, that's enough to show that the integral from 1 to infinity of 1 plus e to the negative x over x is also divergent. Again, we can sort of think of this as saying that since the area under the graph of 1 over x is equal to infinity, then the area under the graph of 1 plus e to the negative x over x is bigger than infinity, so it must also be infinity. So it must also diverge.